Suppose R and S are equivalence relations on a set A, and let T be the intersection of those two relations. Part A, prove that T is an equivalence relation on A. Alright, well, this basically follows from exercise 14 in section 4.3, which had us prove that if we had two reflexive relations, then their intersection is reflexive, and two symmetric relations have an intersection that's symmetric, and two transitive relations have an intersection which is transitive, right? So basically those three properties of equivalence relations are preserved. And then I guess you might want to verify that T is actually a relation on A to begin with, but that's pretty clear because we know that R and S are both subsets of A times A, right? And so it stands to reason that their intersection is also a subset of A times A. Okay, you could prove that pretty easily if you wanted to, but that's how you get that T is in fact a relation on A, and then, like I said, the rest of the equivalence relation proof would follow from exercise 14 in the previous section. All right, so the main thing I want to focus on here are parts B and C. And in part B, we're supposed to show that the T equivalence class of an element X in A is equal to the intersection of the R equivalence class with the S equivalence class. And so one way to think about this would be, what does it mean for Y to be an element of the T equivalence class of X? It basically means that Y is related to X by T, okay? Or the ordered pair YX is contained in T, and that means that it's contained in R and S, right? So Y is related to X by R and by S, and that's exactly what it means for Y to be in the right side here, right? It means that Y is in the R equivalence class, so Y is related to X by R, and Y is in this equivalence class, so Y is related to X by S. All right, so I think this is believable, and you'll see that's basically what happens when we work out the logic. So, okay, here is what we know, and this third one's from part A, and here's what we're trying to prove. So let X be an arbitrary element of A. We're going to prove this equality by, for an arbitrary Y, showing that Y is in the left side if and only if it's in the right side. Okay, and so I want to do that with the chain of if and only ifs. And okay, so let X be an arbitrary element of A. If you want, you can say let Y be arbitrary. We show that Y is in X bracket T if and only if Y is in the intersection here. All right, so here it goes. Y is in X bracket T if and only if Y Tx, if and only if Yx is in T. And then T is defined to be the intersection of the relations R and S. And okay, so if Yx is in that intersection, then we know Yx is in R and it's in S. Or just changing notation YRx and YSx. And each of those means that, okay, Y is in the equivalence class of X with respect to R, and Y is in the S equivalence class of X as well. Therefore, Y is in the intersection. Okay? And all that reasoning goes backwards too. These are if and only ifs, so we are done with part B. Okay. Part C is the kind of cool one. So we have previously defined in a previous problem the sort of dot product f dot g of two partitions, which gives us a new partition, right? It's sort of a refinement of the original two. That's what you get by intersecting one element from the partition F with another element from the partition G. And we are supposed to prove that the partition A modulo T, right? We've proved that T is an equivalence class, so an equivalence relation, so we know that this, which is the set of all T equivalence classes, is a partition of A. So show that that partition is the dot product of the partition you get from the relation R with the partition you get from the relation S. Okay, so the way I sort of picture this is we have this sort of one-to-one correspondence between equivalence relations on the one side, it says equivalence relations, and partitions on the other side. And we are starting out with a couple relations R and S, and we get partitions by looking at the set of equivalence classes of those, right? So this one gives us the partition A modulo R, and this one gives us the partition A modulo S. And now with two equivalence relations, they're relations, right? They're just sets of ordered pairs, so we know we can intersect them to get a new relation. Right? And over here we have two partitions, and we know that we can take the dot product of them, right? Using that definition up there. So that would be A modulo R dot A modulo S. Okay, and the cool thing is that this operation of intersection over here corresponds to this operation of dot product over here. In fact, that's really why this dot product operation on partitions is defined. Okay, to have a counterpart to the intersection for equivalence relations. So that's one way of understanding what this is. Another way is just to sort of write this out, replacing T by R intersect S. This says that A modulo R intersect S is equal to A modulo R dotted with A modulo S. Okay, so there's sort of a nice symmetry to that now. You see how the intersection corresponds to the dot product here. All right, well let's get to work on part C. So again, we have our givens and then our result from part A. And here's a statement we're trying to prove. So we will show that for all sets capital Z, Z's in A modulo T if and only if it's in the dot product of these two. All right, so let's do the forwards direction first. And by the way, I'll bring the proof up here so you can refer to it as we go if you like. We do direct proof, so we bring over a new given. And we write out the definition of Z being in the dot product, right, using this definition right up here. So that tells us that Z is non-empty, and then it's the intersection of some x and y, where x is in the first family A mod R, and y is in the second family A mod S. Right? So these are my F and my G from the definition up there. Okay, well for Z to be in here, this is the set of equivalence class, set of T equivalence classes of A, right? So this means that Z is equal to an equivalence class. Of some element in A, right? So we can say there exists some little Z in A such that Z is equal to its equivalence class with respect to the relation T. And we can do existential instantiation on that to, well, pardon me, before we do that, we can use part B, right, which is where it's vanished from here, but that's where we showed that Z bracket T is Z bracket R intersect Z bracket S. Okay, and then we can split up the conjunction on our goals side. And here's where I do existential instantiation to get a Z naught in A such that capital Z is the intersection of these two equivalence classes. And because Z naught is an A, well, okay, so why am I doing this? I'm looking over here at my goals, and I see that trying to find sort of equivalence class, an R equivalence class and an S equivalence class such that Z is the intersection of the two. Well, that's basically what I have right here, right? So I'm just trying to sort of make that clear. So I'm saying that, yes, this first thing is an R equivalence class, and the second thing is an S equivalence class by definition. And so, well, I also have that, let's see, because, what am I saying here? Z naught, okay, this is just a statement that Z naught is in both of these because Z naught is related to itself by R and related to itself by S. That's because R and S are reflexive, right? And so there okay, and this intersection is equal to capital Z, so I've found an element that's in capital Z, so it's certainly non-empty. And as for the second goal, that comes from these, right? We've found this would be the capital X, this would be the capital Y, such that Z is capital X intersect capital Y. All right, so that would give us this part of the proof right here. And then we got to go the other direction too, right? So suppose we have Z in the dot product, we want to show that z is in A mod t. So this will probably be relatively similar. We read out the definition of z being an equivalence class of t, right? There's some little z in A such that z is its equivalence class. And we use the definition of dot product again, just like before. And we break that up into the first part here, and then we do a couple existential instantiations to get some x naught and y naught in the appropriate sets of equivalence classes such that z is equal to their intersection. Okay. Now, because z is non-empty, we know that it has some element, so let's go ahead and do that existential instantiation to get a little z naught. And combining those two, basically replacing the capital Z up here by what we know it's equal to, we get that z naught is in this intersection. Okay? Therefore, it's in both sets. And combining that with the fact that we know x naught is an R equivalence class, well, we also know an element of it, right? And so it must be the equivalence class of that element. Okay? X naught must be z naught bracket R. And similarly, because z naught is in y naught, and y naught is an equivalence class with respect to S, y naught must be the equivalence class of that element. Okay? There's a couple steps there that are hidden, but I think that's pretty believable, and you can fill in the missing step or two if you like. Alright, so that means we're just about there, because we can replace the x naught and y naught in this equation to get that capital Z is the intersection of these two equivalence classes. And then finally, using part B, we know that that intersection is just the equivalence class of little z naught with respect to t. Okay, so and oh, there's one more thing. Okay, so we also are noting that because these guys are equivalence classes of the set in the set A, they're subsets of A, and that tells us that little z naught is in A. Okay, that's going to be important because we're supposed to show that there exists a z in A. Right, so we have that. There exists a z in A, namely z naught, such that capital Z is its equivalence class with respect to t. Okay. So go ahead and pause the video if you like and see how I wrote that up over here. And that does it.